Distinguished guests, ladies and gentlemen, let me introduce myself. My name is Nanang Triagung Edi Hermawan. I am a doctoral student at Department of Computer Science and Electronics, Faculty of Mathematics and Natural Science, Gadjah Mada University, Yogyakarta. In this session, I will present my short paper on multi-prime number principle to expand implementation of Chinese remainder theorem on an RSA algorithm. Our research was supported by Mr. Edi Winarko and Mr. Ahmad Ashari. They are both of staff in Department of Computer Science and Electronics, Faculty of Mathematics and Natural Science, Gadjah Mada University, Yogyakarta. Let me introduce about the background of our research. We know that the Chinese remainder theorem method can be combined and implemented in an RSA cryptography algorithm system. It is very useful to speed up, especially in decryption processing. The combination method implementation with such a Python 3 programming language, we use some little module to find or to calculate an inverse modulo of some prime numbers, but in some size of a prime number, in bits of course, we get some problem. The modulo generates some recursion error, and we cannot implement our calculation of our algorithm. So our research goal is to solve the above recursion error by implementing multi-prime number of an RSA algorithm. In this slides, I will tell you about our proposed methods. We know that an RSA algorithm generates a random key, especially public key and private key, based on only two prime numbers. But to expand the implementation of a Chinese remainder theorem, we improve the standard RSA algorithm by multi-prime numbers. We implement not only based on two prime numbers, but we implement based on 4 prime numbers, 8 prime numbers, 16 prime numbers, and also 32 prime numbers. And our improved RSA algorithm, the first one, we generate random prime numbers by 4 prime numbers, 8 prime numbers, 16 prime numbers, and also 32 prime numbers. And then from each of prime numbers, we calculate modulo number as a result of multiplication of each generated prime numbers. After that, we calculate Euler rotation that we use to find a number, a co-prime number of our modulo, an algorithm improving RSA. After that, we establish the public key. And from established public key, we can find a private key by calculate an inverse modulo of public k on the modulo of Euler-Totian numbers, and then we can calculate, of course, an Euler Chinese remainder components as a component of private k that we will use to decrypt or to implement of CRT methods in the decryption processing. And after that, we got public key and private key, and of course its private key component, we can use it to encrypt of our message. It is not different in encryption processing with the standard RSA. We can use the formula of standard RSA. After we get ciphertext from plain text in encryption processing, then we conduct decryption processing to change our ciphertext to find plain text again. In this processing, we use all of private key component to simplify the calculation of decryption process. The model implemented in Python 3 language programming by varying the size of k from 800, 1045 until 8192 bits. From the running program, then we analyze duration of random key generation, encryption, decryption as a performance of our improved model. And now we can see the result and discard it. In random key generation performance, we know by implemented multi-prime numbers, we can expand. If we use standard RSA based on 2 prime numbers, we can only implement it, the Python programming, up to 3200 bits. But by expand based on 4 prime numbers, we can reach 6000 key bits. And then if we use 8 prime numbers, we can expand until 12,000 bits. And then in the second figure, we can also see we can expand more again. If we use 32 prime numbers, we can implement our Python program until more than 50,000 bits. Of course, by implementing of multi-prime number, we can expand the implementation of RSA algorithm in Python programming. In encryption and decryption performance, we can look from the graph. It also can expand the cases of our algorithm, and especially in decryption performance, we can look by multi-prime numbers. We can speed up our decryption processing in varying of cases of our improved algorithm. So from our presentation, we can conclude our research that a modified RSA implementation by implementing multi-prime numbers combined with Chinese remainder theorem method can solve the recursion error problem that we find in our Python 3 language programming. The second, increasing on a number of used prime numbers expands executed longer case sizes. And the third, utilization of multi-prime numbers can speed up random key generation and decryption processing very significantly. That's our presentation. Thank you so much for your attention and nice to meet you. Thank you very much.